so that principal ma'am will join. Then we will
Okay.
start the session.
Okay, ma'am. Thank you.
NIT Patna and research interest in different fields like semiconductor device modeling and simulation, emerging devices, JLT, TFET, FinFET, VLSI design, and meta surface or meta material devices like this. And today topic is very thank you to attend our BCE platform, Dr. Pankaj Kumar, NIT Patna. And first of all, and research interest, I am very happy in different fields. Select like college, semiconductor device modeling on the topic simulation, materials and emerging devices, technology, JLT. Do you know about students? Asking to you, semiconductor material design. People knows from first year. And what is meta surface or meta property material devices? But when lecture delivered by the specific and today topic is very thank you to attend whatever you have learned already platform up to this time. Definitely you will add it. Pankaj Kumar, NIT Patna. And first of all, and research interest, I am very happy in different fields like college, semiconductor device modeling, on the top simulation, materials and emerging devices, technology, JLT. Do you know about students? Asking nanostructure, semiconductor material design from first year, and what is meta surface or meta property material devices convert into nanostructure. Lecture delivered by the, for example, today topic is thank you to attend whatever you have learned already platform up to this time. Microstructure added Pankaj Kumar, all the property. And first of all, and research interest, I am very happy in different fields like college, semiconductor device modeling, on the top simulation, materials and emerging devices, technology, JLT. Do you know about another properties also change? So these are the analysis. But how you will change the in nanostructure? So for that X, Y and Z all three डायमेंशन होता है ना, उसको आप चेंज करके नैनो साइज में लाना है. तो उसका पूरा पैरामीटर होगा कि इस वैल्यू को 10 to the power 6 10 to the power -9 में लाना है. तो व्हाट यू विल डू? तो फॉर एग्जांपल एक्स जो आपका एक्सिस है, अगर आपने कोई स्टैंडर्ड यूनिट लिया हुआ है तो उसको एक चेंज करो. मान लो एक क्यूबिक है, एरिया 111 ले लिया आपने, उसको नैनो में ले जाना है. देन व्हाट यू विल डू? अगर मान लीजिए केवल एक एक्सिस को शॉर्ट किया, बट हाउ यू विल change in nanostructure? So for that X, Y and Z all three बाकी सिलेक्शन होता है ना, उसको आप चेंज करके नैनो साइज में लाना है. And that is analysis by not plus 10 to the power 6. That analysis 10 to the power -9 में लाना है. So what you will do? That's for example X1 X जो आपका एक्सिस है, अगर आपने कोई स्टैंडर्ड यूनिट लिया हुआ है उसको एक चेंज करो. मान लो एक क्यूबिक है, एरिया 111 ले लिया आपने, उसको नैनो में ले जाना है. देन वो कन्वर्ट, मान लीजिए केवल एक एक्सिस को शॉर्ट किया, बट हाउ यू विल चेंज in nanostructure? This X, Y and Z बाकी सिलेक्शन होता है ना, उसको आप चेंज करके नैनो साइज में लाना है. And that is analysis by not plus 10 to the power 6 relatives analysis 10 to the power -9 में लाना है. Can you what you that's for example X1 reason is there आता है जो आपका तो एक्सिस है, अगर आपने कोई स्टैंडर्ड यूनिट लिया हुआ है घर पे उसको एक चेंज करो. मान लो एक क्यूबिक एरिया 111 ले लिया आपने, उसको नैनो में ले जाना है. कन्वर्ट, मान लीजिए केवल एक्सिस को शॉर्ट किया, बट हाउ यू विल चेंज द एक्सिस का नैनो से लिस्ट है ना, निकाल के उसको जलाते हैं, उसके ऊपर एक पॉट रख देते हैं, जो स्ट्रक्चर डेवलप होता है जो कार्बन का, दैट इज नैनोसाइज. एनालिसिस किया तो पता चला. तो व्हाट मेरा ये कहना है कि आप कोई भी सब्जेक्ट से अछूते नहीं रहना चाहिए. आपके जरूरी नहीं है कि वो सब्जेक्ट मटेरियल में ही पढ़ना हो. यू हैव टू नो इन डिटेल्स बिकॉज यू आर अ स्टूडेंट ऑफ इंजीनियरिंग स्टूडेंट है आप. तो उसके लिए आपको क्या करना है कि हर चीज के बारे में थोड़ी जानकारी होनी चाहिए. ओके. कोई भी सब्जेक्ट से अछूते नहीं रहना चाहिए. आपके जरूरी नहीं है कि वो सब्जेक्ट मटेरियल में ही पढ़ना हो. यू हैव टू नो इन डिटेल्स बिकॉज यू आर अ स्टूडेंट ऑफ इंजीनियरिंग स्टूडेंट है आप. तो उसके लिए आपको क्या करना है कि हर चीज के बारे में थोड़ी जानकारी होनी चाहिए. ओके.
Hello, ma'am, your voice is not audible. Hello.
जलाते हैं उसके ऊपर एक पॉट रख देते हैं.
I think ma'am has left the
होता है जो कार्बन का एनालिसिस किया तो पता चला. तो व्हाट मेरा ये कहना है कि आप कोई भी सब्जेक्ट से अछूते नहीं रहना चाहिए. आपके जरूरी नहीं है कि वो सब्जेक्ट मटेरियल में ही पढ़ना हो. यू हैव टू नो इन डिटेल्स बिकॉज यू आर अ स्टूडेंट ऑफ इंजीनियरिंग स्टूडेंट है.
sir, your mic is mute. You are muted.
उसके लिए आपको क्या करना है कि हर चीज के बारे में थोड़ी जानकारी.
Okay, so maybe due to some internet connectivity issue, ma'am has left the meeting. So I guess we can start the expert talk. I welcome Dr. Pankaj Kumar sir. Thank you sir for accepting our invitation and giving and presenting your talk to our students. So thank you sir. I hand over it to you. Sir, you can start the presentation. Sir, please.
Thank you, Pushpanji, for inviting me and giving me an opportunity to interact with the students of the Bhagalpur College of Engineering. And I also thank the principal ma'am
Sir, your mic is mute.
for introducing me and also giving the detailed overview of the
Okay, so maybe
nanotechnology.
due to some internet connectivity issue,
So now I will start from the basics of semiconductor materials and move on to.
I welcome Dr. Pankaj Kumar sir. Thank you sir for
So
accepting
I
our
hope that
invitation
my screen is visible.
and presenting your talk to our students. So thank you sir. I hand over it to you. So you can start the presentation. Sir, please.
Thank you, Pushpanji, for inviting me and giving me an opportunity to interact with the students of the Bhagalpur College of Engineering. And I also thank the principal ma'am
Sir, your mic is mute.
for introducing me and also giving the detailed. Pushpanji, my screen is visible to all of you.
Yes sir, it's visible.
Now I will start. Okay. So I have not prepared a slide since that's become very monotonous. I've been interacting with the students, so I will go step by step. So if any student find difficulty in any stage, they can just ask the questions in mid also, and in last also they can ask. Okay. So I will start from this semiconductor. What is semiconductor and what's its use? What is semiconductor? So Pushpanji, my screen is visible to all of you, and why it is so popular. Okay. So I have not prepared a slide since that's become very popular. So I will go step by step. So first, any student find what is semiconductor? So on the basis of resistivity, and in last also they can ask. Okay. We divide all the materials into three categories. First one metal, semiconductor, and what's its use. Second one semiconductor. What is semiconductor? And third one insulator. So my screen is visible to all of you, and why it is so popular. Okay. So if you will look into the metal, let us take the example of. So first, some of the what is semiconductor. So on the basis of resistivity, and in last also they can ask. Okay. We divide all the materials into three categories. First one metal, semiconductor, and what's its use. Second one semiconductor. What is semiconductor? And third one insulator. See, just for metal, let us take the example of few metals like gold, copper. Look into the metal. Just take the example of. So first, some of the what is semiconductor. So which one has the highest conductivity? Gold, copper, or platinum? So if we will see the resistivity, then we will find that the copper has a resistivity of 16.8 into 10 to the power minus 9 ohm per meter. And for gold, platinum. So if we will see the resistivity, then we will find that the copper has a resistivity of 16.8 into 10 to the power minus 9 ohm per meter. And for gold, for metal, let us take the example of few metals like gold, copper, metal, platinum. So this one has the highest conductivity, gold, copper or platinum. So if we will see the resistivity, then we will find that the copper has a resistivity of 16.8 into 10 to the power minus 9 ohm per meter. And for gold, for metal, let us take the example of few metals like gold, copper, metal, platinum. So this one has the highest conductivity, gold, copper or platinum. So if we will see the resistivity, then we will find that the copper has a resistivity of 16.8 into 10 to the power minus 9 ohm per meter. And for gold, for metal, let us take the example of few metals like gold, copper, metal, platinum. So this one has the highest conductivity, gold, copper or platinum. So if we will see the resistivity, then we will find that the copper has a resistivity of 16.8 into 10 to the power.
And another one is the compound semiconductor. Elemental semiconductors are like silicon, germanium, or group 4 metals. They are the elemental semiconductors. What are the compound semiconductors? They are the semiconductors which are a compound like gallium arsenide. Okay. So in compound semiconductor, again we have two categories. In compound semiconductor, we have two different classification. One having a covalent bond and another having a ionic bond. Elemental semiconductors are like silicon, right? Germanium or group 4 metals. So in covalent bonds, what are the compound semiconductor having covalent bonds? When we add a group 3 element with the group 5 element like gallium arsenide, okay, gallium nitride. In compound semiconductor, so in these are there are the covalent bonding between gallium and arsenide. But when we add group 2 element with the group 6 element, okay, then also semiconductor will be formed. These are the compound semiconductors. So examples of these are zinc sulfide. What are the compound semiconductor having covalent bonds? When we add gallium sulfide, so these form the ionic bond. Okay, gallium arsenide. So in this way we have classified our semiconductor into these two groups. So in these are the and another way of bonding between gallium and arsenide. But when we add classifying semiconductors is based on the energy gap. Okay, then also semiconductor will be like one way is that the semiconductor which has a direct band gap. Another semiconductor which has an indirect band gap. So these are these form the ionic bond. Okay, so most of the elemental semiconductor falls in the category of indirect band gap semiconductors. Okay, and
most of the compound semiconductor falls in the category of compound semiconductor, but not all the compound semiconductors are having a direct band gap. That we should keep in mind here. Okay, like another semiconductor indirect band we can silicon, germanium. These all have an indirect band gap, and like gallium arsenide. So most of the elements have the direct band gap. Some of the compound semiconductors which also have the indirect band gap are the semiconductors, gallium phosphide. And most of the compound semiconductors fall. So in this way we can classify our semiconductors. So these all are the categories of pure semiconductors. Okay. Like then there comes another category, that is crystalline and amorphous, and like gallium arsenide. So most of the elements have the direct band gap. Some of the compound semiconductors which also have the indirect band gap are the semiconductors, gallium phosphide. And most of the compound semiconductors fall. Okay, so we can also categorize our semiconductor in the form of most of our semiconductor are of the crystalline in nature. Crystalline in nature means semiconductor to the smallest unit is called the lattice size. Suppose this is the smallest unit of semiconductors, and this is being repeated to form materials. So these units are identical in nature. When these all units are identical in nature in all the x and y and z directions, then they are called the crystalline semiconductor. But when these are not symmetrical, then that leads to the amorphous semiconductor. Most of our semiconductor are of the crystalline. And once we do the doping, then we divide semiconductor into two types: degenerate semiconductor and non-degenerate. Okay, that we will discuss later once we go for the doping. Right? So now let us come to the our topic: doping of semiconductor. Identical in nature. When these all units are identical in nature in all the x and y and z directions, then they are called the crystalline semiconductor. But when these are not doping for elemental semiconductors are in a different ways, and doping of compound semiconductors are done in different manners. So degenerate semiconductor and non-elemental semiconductors and compound semiconductors, the doping process are completely different. Okay, so now let us come here. In elemental semiconductors, what we actually do, we generally dope our this semiconductor with some impurities, like suppose this elemental semiconductor will be of group 4 element. So if you want to dope this semiconductor, then either we can add from group 5 or we can add impurities from group 3rd. Okay, once we add these materials into this, that is called the doping of semiconductors, and the conductivity of semiconductor increases. That also you will see in detail why after doping the conductivity increases. But in compound semiconductor, this is called substitutional doping. Impurities, like suppose this elemental semiconductor will be of group 4 element. So if you want to dope this semiconductor, in this type of semiconductor, we generally dope with group 5 or 4 semiconductors. Okay, suppose this is gallium arsenide, and I will dope this with a silicon. Let's suppose. Then this silicon has the two options. Either it will replace gallium arsenide or it will replace arsenic. So depending upon this silicon replaces which gallium or arsenide, the doping can be of N type and P type. Okay, but in elemental semiconductor, when we dope with this pentavalent item, then it is N type, and once we dope with the third group element, then it is a P type. Gallium arsenide
semiconductor,
A pure silicon,
right?
a pure silicon atom.
Why you need to dope
Carrier concentration.
impurities? So, in a 1 centimeter cube, if you will see that the number of silicon atoms present, that's in the range of 10 to the power 23 per centimeter cube. This much number of silicon atoms are present in a 1 centimeter cube of dimension. So now if you will compare this with the intrinsic carrier concentration, say to the power 10, then it is very less.
But then also,
One charge carrier in around 10 to the power 13 silicon atom.
right? A pure silicon atom. Why you need to dope carrier concentration?
That's why the conductivity of pure silicon is very less and it cannot be used in its pure form. Okay, so we have developed a way to increase the carrier concentration, with the help of a doping. So let us dope this silicon atom with phosphorus atom, that is of group 5 element, and this is of group 4 element, right? And now we will see what happens after doping, why the conductivity increases. So let us draw the, this is silicon, is a group 4 element, and it forms a covalent bond, right, with 4 silicon atom. If you find any difficulty in, then you can ask question at the same time. No need to wait for the question session. Phosphorus atom, that is of group 5 element, and this is of group 4 element, right? And now we will see what happens after doping, why the conductivity is a very basic thing you might be knowing. You might have studied this in the first semester or the second semester, but still, once the specs comes, then I find that they have a basic difficulties in the basic things. If you find any difficulty in, then you can ask question at the same time. No need to wait. Like, suppose this is a silicon atom lattice. So what we see that each silicon atom is surrounded by these 4 silicon atoms, right? Now what we do, we dope this silicon atom with phosphorus atom, right? Let the doping concentration be 10 to the power 18 per centimeter cube, right? Let this should be the doping concentration. What does that mean? This means that this much number of phosphorus atom per centimeter cube is mixed with the silicon atom. So what will happen? This phosphorus atom will suppose replace this silicon atom. And let us have now phosphorus atom. Okay. Similarly, all these phosphorus atom will get placed somewhere. Okay. So now what we found that this has 5 electron at its outermost shell. So 4 electron will make pairing with 4 silicon atom. Okay. And still it has 1 electron with it. Okay. So till now the conductivity has not
energy can be given in the form of temperature after the doping. Right? So how to remove this electron? In order to remove this electron, we need an energy. So either this energy can be comes for the p-type semiconductor. As here we have seen of n-type, in the same way in p-type semiconductor we dope this with a boron atom. Right? So once we dope this with boron atom, then what happened? So once this boron atom will come here, suppose a boron atom will come. We know that boron atom has 3 electrons in its outermost shell. So then this boron will make covalent bonding with 3 semiconductor. Right? And this bond is not formed. Okay, then from where the holes are generated? In that case, we have seen that. Can anyone answer? Since we have doped this silicon with boron atom, and this boron has only 3 outermost shell electrons, which already makes covalent bond with 3 silicon atoms. Then how the holes are generated and not the electrons are generated? So again here, what will happen, since this bond is not complete, so what will happen, There are two bands, conduction band and valence band. Valence band are completely filled and conduction band has a free electron. So what will happen? Electron from this conduction band, this valence band will come here and will make a bond with this silicon atom. Will make a bond with this silicon atom. And in this case, since this electron has come from valence band, so a hole will be generated in the valence band. So as many number of boron atoms are present here, same number of holes will come, electrons will come from this valence band and will make pair with silicon atom, and as many number of holes are generated. So in p-type doping, only the concentration of hole increases. As we have seen in n-type, only the concentration of electron increases, not the hole. In the same manner, here we have seen that only the concentration of hole increases and not the electron. So in this way, the carrier concentration increases and the conductivity becomes high. Okay. So now we have seen that how to manipulate the conductivity of semiconductors. Okay, and this manipulations of conductivity is not possible with the metal, right? Therefore, metal is not used. Here we can control the conductivity once with the help of this temperature, with the help of doping, and there are so many other ways to control the conductivity. That's why semiconductor is so popular and it is so useful. So if we'll calculate the conductivity after doping, then we can see that how much the conductivity increases. So let us take intrinsic silicon atom at room temperature, 300 Kelvin, right? And if we will dope this with a pentavalent Nd, 10 to the power 18, and then if we will compare its resistive in conductivity, then we will find that with respect to intrinsic, its conductivity becomes very high. Okay. Next thing to understand in semiconductor is the Fermi level. Okay. Now we came to know about what is semiconductor, how we can classify semiconductor, and how we can use semiconductor for our application by increasing its conductivity, either increasing the concentration of hole or either increasing the concentration of electron, right? Now there are, we can generally each materials have a conduction band and a valence band. Okay, and these two bands are separated. That is called the band gap. Okay. On the basis of this band gap, we can also classify materials like insulator will have a large band gap. This AC will be very high for insulator. AC will be greater than 5 electron volt in the case of insulator. In the case of metal, this band overlaps each other. In the case of semiconductors, this band is in the less than 5 electron volt. So for silicon, this band gap is near about 1.1 electron volt. And one more thing, suppose a silicon atom is there, and if we dope this with both p-type and n-type, p-type, if it means we dope with a pentavalent or trivalent, means from group 5 element and group 3rd elements, then it will become n-type or p-type. That depends upon the concentration of these impurities. Whose concentration is higher will dominate here. If you have any doubt till now, you can ask. Then there comes the density of state in semiconductor.
Sir, hello. I have one doubt.
Yeah, sure.
Sir, if semiconductor have both concentration of P type and N
Right,
type,
right,
then known as compensated semiconductor, right?
right. It
Then
is called
how
a
can
compensation doping.
yeah?
Yes.
So how can you define like which is N type or P type?
See.
It should be like only the
Right.
electron impurity or majority of
Suppose
things.
right. Suppose Na is the doping concentration of trivalent, okay, and Nd is the doping concentration by pentavalent, okay, and we are doping silicon with both of them, right?
Yeah.
So in this case, two case can be in this type. There can be two case. Case one where Nd is greater than Na. So in this case, this will become overall N-type. And the concentration of electron will be Nd minus Na. Okay, and the concentration of hole will be here intrinsic carrier concentration divided by Nd minus Na. Case 2 can be where Na is greater than Nd. So this will be a p-type semiconductor. Right?
Take some condition like the density should be greater than 10 to the power 5.
Whose density?
Like Na density for case 1, Nd density should be greater than 10 to the 5 Na. Then we can say that Na is equal to Nd minus Na, or P is equal to Ni square upon Nd minus Na.
Right. Once this is much greater, then there is difference much, but once this will be approximately same, then we can't say that which
Yeah,
type will
but
be.
for that there is different formula.
Right. For there is a different formula. Okay.
Okay, thank you.
And on the basis of this doping only, we have the two different semiconductors, that is degenerate and non-degenerate semiconductors. So how we will define the degenerate and non-degenerate semiconductor? There are two things: density of state. Density of states means once electrons occupy any states, then at each is one place, two electron can occupy, that having the opposite spins. So once we draw the EK diagram, that is energy and momentum diagram, then what we see that for once this electron will come to here, it has a definite place everywhere with once energy increases, this also increases. With respect to this K, we have a different levels of energy, and at that place electron can occupy. That is called the density of states. Means available states where electron can occupy. Okay, number of available states per unit energy per unit volume. So density of states is number of available states per unit energy per unit volume. So these are constants. These are like NC and NV. You might have used this in the formula. So these are also in the range of near about 10 to the power 23 per centimeter cube. So when we dope our semiconductor and our doping concentration is approximately equal to this density of state, in that case what we say that this is a degenerate semiconductors, means that acts like a metal, conductivity is very high in that case. So if Na and Nd if Na and Nd is much less than Nc and Nv, Nc is the density of a state in the conduction band and Nv is the density of a state in the valence band. Then this type of semiconductor is called non-degenerate semiconductor. Non-degenerate semiconductor. Okay, but if we will increase this Na and Nd, and if this become approximately equal to Na and Nd become approximately equal to Nc and Nv, in that case these are called the degenerate semiconductor. Okay, so in this case, as we know that Na and Nd are very high, that means the conductivity will be very high. So in this case, conductivity is very high and it's can act similar to the metal, and these are similar to metals. Okay, and in amorphous, again I have discussed that we have the two different types of semiconductor, crystalline or amorphous. So in crystalline, we have a discrete space between these two conduction band, valence band and conduction band. There is no available state. Suppose this is your EC and this is your EV. EC and this is your EV. So this is a band gap, EG. What does band gap means? There is no available state for electron to occupy. Means there is no density of states available for electron to occupy. So in crystalline, there is no state. But in amorphous, what we find that density of state, some of density of state also lies in the band gap. So what happens? These act as a defect, and some of the electrons get trapped in this defects that are mostly the dangling bonds. Okay, so this also we have to keep in mind that There are two different types of semiconductor, and few other terms like
Sir, any example of degenerate semiconductors?
you just dope semiconductor with a very high conductivity, then this will become a degenerate semiconductor. Doping generally the doping concentration we take near about 10 to the power 18 to mostly maximum to 21, because on the basis of doping concentration also there are so many effects. Once we just dope this to make our MOSFET or transistors. So if you increase the concentration of this, then there are so many sorts of effects occurring in that MOSFET also. So generally we keep this less than the 21, less than 20. Most of the doping you will see find in that book that it is near about 10 to the power 16 we go for the p-type semiconductor, and is 18, 19 or 20 we go for the n-type semiconductors. If we increase the doping concentration to 22 or 23, then it will become a degenerate semiconductor and conductivity will be very high. Okay.
Okay, sir.
And now I will talk something about the Fermi level. And then we'll move to the density of state again, and then move to the quantum well. So how can we define a Fermi level? Generally, a Fermi level is defined as the probability of finding of electron at that Fermi level is near about 0.5. So, in the case of pure semiconductor, what we can see that Fermi level is just midway of the two band. Another important Fermi level. So let's suppose this is the conduction band ECE and this is the valence band EV. And in the case of pure semiconductors, and we assume that the mass of electron and the mass of hole are near about same, but these are not actually same. Mass of electron and mass of hole are different because this depends upon the how the density of states or energy level in the conduction in the valence band. Since the slopes are different, since the slope of the conduction band, this is conduction slope of this and this are different. Therefore, the mass of electrons and holes are also different for materials. So let us assume this to be identically same. So in that case, we define a level that is midway of this EC and AV that we call as a Fermi level intrinsic, right? So in a pure semiconductors, there will be a conduction band, there will be a valence band and a Fermi level. The electron, once will hit that pure semiconductors, electron will generate at this point and it will travel to the conduction band. It will travel to the conduction band, right? And after some time, again this electron will come to the valence band. Okay, this will not remain here forever. So once this will lose energy, it will again come to the valence band, right? In the same manner, all the holes, how we define as a holes? We generally define holes as air bubble. Okay. So holes always occupies on the top of your valence band. Holes are what? Holes are the empty state of electron. somebody can ask you that why the holes are on the top of the valence band. So we can very easily say that since the electron always occupies to have a least energy states, electron tries to move towards the least energy states. Therefore, suppose here is electron, it will goes down. Again, it will goes down. So all the electrons will come down, and holes, vacancy of electron will be at the top. So holes are at the topmost of your valence band, and in midway we define as a Fermi level. Now, once we dope these semiconductors, right? Then what happens? After doping, now let us dope with the pentavalent, that is lot n-type. N-type semiconductors. So here, there will be a conduction band, and again there will be a valence band. Now, these were the Fermi level, intrinsic Fermi level condition value. Now what happened? Now we have doped this with a pentavalent atom. So number of electrons increases. Okay. So what will happen? A new Fermi level will be formed, and that will be the close to this conduction band, because now we have a more number of electrons. So this will be called as a new Fermi level. That is E of Fn. Okay. And if we will dope this with a p-type semiconductor, so in that case, what will happen? In p-type semiconductors, the concentration of hole will increase and concentration of electron will decrease. Therefore, this Fermi level will come closer to the valence band. This will be your E of F of P. Right? So that's why when we connect a p-type semiconductor with an n-type semiconductor, a junction is formed. Okay, so there can be two different type of junctions. One can be termed as a homojunction, and another can be termed as a heterojunction. In homojunction, what happened? The same type of semiconductor form the junction. Suppose I will make a junction with silicon having n-type silicon with a p-type silicon. With a p-type silicon. Then this junction is called the homojunction, because both the materials are of silicon. And if we will just make a junction with a silicon with that of a germanium, silicon with that of a germanium, then this is called the heterojunctions. So what actually I want to say that whenever we just make a junction with two different type of semiconductors, in that case also you will have a constant Fermi level throughout. Right? Fermi level will not change. Fermi level will remain same until when we applied any external voltage or electric field. So let us see. You might have seen this type of. Let us take a n-type. This is n-type silicon and this is p-type silicon. Okay. So what I have told that since we have not applied any external, we have not connected with this some any external voltage source, right? So this is open. So in that case, what will happen? Both the Fermi level of this and Fermi level of this, that we have seen that in Fermi level n-type, Fermi level is close to the conduction band, and here Fermi level is close to the valence band. So once we connect both of them, in that case, Fermi level will remain same, right? So here what we see that, this Fermi level will remain same for both the materials here, and accordingly we have to draw the, since it is n-type, so in this case conduction band will be near to this Fermi level. Let's suppose this is a Fermi level, right? And this is a p-type semiconductors. So in this case, and let this to be the EC, and this will be the EV of this side. Let us only look at this n-type semiconductors. In this way we can make it. So, and for this, how we can make? Fermi level will be close to valence band, and its conduction band will be away from. So like this we can just make the Fermi level of any materials if it is said. Okay, so like this is the Fermi level. What is this? This is your diode. Okay, and this is your junction, right? Now you see here the concentration of electron at this side is high, and the concentration of hole at this side is high. So at the therefore once we make the junction of a semiconductor, what will happen? There will be the change in the concentration of electrons in the hole, and in the same manner, therefore diffusion of electrons in holes will take place. That's why there develops a depletion width in a diode, and this depletion width becomes constant after some time because of electric field developed, which further opposes the movement of electrons and holes from each other. Okay, so this is a short introduction of Fermi level, and any doubt in this Fermi level, how to just make a Fermi level of semiconductors?
No, sir.
Okay. Now we will move the density of a state, that is most important. So we generally denotes density of states in the term of rho k or rho e, right? Here k is a space vector. It is a vector quantity. So if you will take a rho k dk, that means number of states between k and k plus dk per unit volume of the material. Okay. Similarly, this rho e and dE also has the same meaning. The number of states between E and E plus dA per unit volume of the materials, right? So what you will find that this rho k dk is same as rho e dE. Okay, so I will again illustrate this with the help of a graph. This is the valence band, this is your conduction band, and this is your k vector, and this is your energy. So with respect to each and every point here, each and every point of k, we have a respective energy level. Suppose this is the energy level. Let this to be a k, and this point should be k plus dk. K plus dk. So between k plus dk, this much number of density of states are there, right? And here what is there? Energy E corresponding to k, and corresponding to k plus dk, what is we have? E plus dE. So if we'll see from here, so if we move from E to E plus dE, same density of states are there, in which like we have moved from k to k plus dA. Okay. So if we take the parabolic approximations of this, so energy level we can define as E equal to EC plus H squared K upon twice of ME. ME is the effective mass of electron in conduction band. And for valence shell, this can be written as E minus H squared K upon twice MV, mass of electron in valence band. Okay. So once we come to the quantum mechanism, then what we find that most of the semiconductor crystallines and where atoms are arranged periodically, right? Suppose atoms are arranged periodically. Let's suppose A is the lattice size. Lattice size means smallest cubical unit dimension. Let this to be the A, right? So what we find that this periodically arrangement leads to the periodically potential variation. So this led to the periodically potential variation. There is a periodically potential variation. and motion of electron in crystals are therefore governed by the laws of quantum mechanism. So, because it's very difficult to solve the Schrodinger equation in a solid, so Bloch was a scientist which has stated that potential vary periodically. Therefore, the probability of finding of an electron should also vary periodically. Okay, means the wave function should also vary periodically. Okay, so probability of finding of electron is proportional to the wave function. Right. So F. Bloch have stated that this is a plane wave equations. Plane wave equation. And this is a function of periodic function. Periodic self function. Periodic self function. And A is what? Interatomic cell. So once they have put the value of this in the Schrodinger equation, and then from there, just I am writing this Schrodinger equation in order to show that how the density of a state has been derived from the ECE diagram. So if you write the Schrodinger equation, so what we found that E has also turned out to be periodic. E also turned out to be periodic in K space. Okay. So from this, he proposed that E is also periodic with the function of K. Periodic means what? Periodic means, suppose this is a K, suppose this is a K and this is your energy E. This is your energy E. So, and this is the first period, this is repetition, pi by A. This will be 2 pi by A. And this will be minus 2 pi by A. So this E is a periodic. This E is a periodic. Right? So therefore, whenever we used to represent the ECE diagram, so in book you might only see like this one. Here we represent the K and this we represent the E. Right? This is general representation of the ECE diagram. But in actually, this is a periodic. We are showing only this ECE diagram for one period. So for representation purpose, what we use representation for only one period. So ECE diagram. So ECE diagram of semiconductors can be represented using three different ways. One is periodic zone, another one is a reduced zone, and third one is your extended zone. So reduced zone is what? This one, that gives only the value in minus pi by A to pi by a. Between these two only ones we will show, then that is called the reduced zone. Periodic zones, when we show the complete, that is the periodic zones. And what is extended zone? In extended zone we show more than one period. Suppose this is minus pi by a, 2 pi by a. So for first zone, let's suppose we have represented like this. So here also, then you will represent second zone, and then if you will represent the third zone. So this is the extended zone. So for each and every value of k, there is a corresponding allowed energy state. For each value of k, there is allowed energy state. And that is the solution of Schrodinger equation. Okay, and k is discrete. Here k is discrete. But then also, why we show continuous line? Generally we used to show with a continuous line. But as per our Schrodinger equation, what we found that actually as per the Schrodinger equation, this should be like, suppose this is a k, and so for k is a discrete, so there should be a discrete value. For this point, there should be this, like this. Okay. So in actually this should not be a continuous line, but we used to represent this with a continuous line because the number of values of k is very high. This discrete number of values are so large that it acts like a continuous line. If the number of values will increase, so it will changes to the continuous lines. So in this way, we define the density of a state, this EK diagram. And what is k here? K is a vector. K is the propagation vector, and that corresponds to 2 pi upon lambda, that is de Broglie wavelength. Okay, and since we can also write momentum in the terms of this k, therefore sometimes we also call it as a energy momentum diagram. Okay, therefore we also call this as a energy momentum diagram. And mass of electron and effective mass of electron, how we find that? We find using this formulae from this EK diagram. Therefore this EK diagram is very important for students who want to study the semiconductor. Right. So what you see that this mass depends upon double differentiations of this d by dk. So the slope, if the slope will change, then the mass will change. Therefore, there are different mass for electron and for different mass for hole. Any doubt till now? This energy momentum diagram of a semiconductor. Do you have any doubt, or should I move further?
Sir, please move further.
Okay. So this is energy, and if we plot this as a rho energy, in that case we see that this is a density of a state, that is rho c with respect of E, and in the same way this is your EC, and this is your EV, and here density of states is rho v E. The slope of this density of states in valence band is less. Slope is less because the mass of electron in valence band is greater than the mass of electron in conduction band. Okay. So what we see here, the density of a state is a continuous function. It is a continuous function, right? Because k is a vector, kx, ky, kz, and all the three directions, the k can have its values. Okay. But now once we move to the quantum Welle structures, this is for a bulk material. Bulk material means materials which have dimension in all the three dimensions: x direction, y direction, z directions. Okay. So in that case, what happened, that if you plot the k vector, this is a k vector. So kz, ky, and kx. So there are n number of points in all the directions. There are n number of points in all the directions, right? So if you'll find out at any point the density of a state for rho k and dk, we found that there are very high density of states. Suppose this is rho k dk, and we have seen that there is a high density of state. But once we move from bulk material to a very thin materials, very thin materials, right? So in that case, what will happen? We will not have the value of k in one direction. So in that case, we will have only limited to two direction. So in this case, this is your kz, ky, and kx. So what will happen in this case? Suppose this is your k. You can move only in this plane. Only your k vector can move in this plane. Okay. So there is a discrete number of plane in that. Earlier case, what was there? Everywhere you can move here and there. But now, what has been limited? The only kx and kz can move in this plane. Okay. So number of density of state decreases. So density of state decreases for a very thin sheet. Okay, so depending upon this, the decreasing the dimension, nanotechnology was coined in 1974. Professor Norio at Tokyo University coined the term nanotechnology. Okay, so as the principal ma'am also talked that the color of gold changes to red from yellow. Color of gold changes to red from yellow below the microscopic range. Means once we will suppose this is a bulk gold and initial color of this gold is yellow, and we will start decreasing its dimension. Suppose this direction we start decreasing, and once this direction reaches below the microscopic range and comes to the nano range, in that case the color will change to red. So if a bulk material is changed, then three different structures can be formed. One is quantum well, another can be the quantum wire, or third can be the quantum dot. Okay, as the name suggests, we can just analyze that how this well can be formed. If we will just decrease the dimension in one direction, then a quantum well will be formed. If we will decrease dimension in the two directions, then quantum wire, and if we will decrease dimension in the all the three directions, then the quantum dot can be formed. So let us quantum well. If the two dimension remains that of bulk material and one direct dimension change to nano dimension, then a quantum well is formed. Okay. Similarly, we will also see how the density of a state changes for the quantum well. Then for quantum wire is reduced in 2 dimensions. Reduced in 2 dimensions, and quantum dot is reduced in all the 3 directions. Is reduced in all 3 dimensions. So what happens if the dimensions is changed? The major changes occurs in the thermal and electrical conductivity. Thermal and electrical conductivity. Okay, if we change the dimensions either in 1 direction or in 2 directions or in 3 directions, it will majorly affect the thermal and electrical conductivity of that materials. So generally it becomes very high. Okay, and another property, it also becomes very strong, very hard materials. If we'll change the dimensions to 1 direction, like graphene. Graphene is what? It is 2 dimensional representation of a graphite. So it is a very strong material. So same way, its strength increases. Okay. So now we will see the how the density of states changes in the quantum well structures. Density of a state in quantum well. So if you plot the density of a state, so energy was a function of EC plus H squared K squared by twice MC. Okay. So which could be further written as EC plus Kx squared MC plus H squared Ky squared twice MC plus H squared Kz squared upon twice MC. Okay. So we can also write here K to be the Kt plus Z Kz. What is Kt here? Kt is a transverse vector. Transverse vector, that is x kx plus y ky. So this E can be written as EC plus E with some q equal to 1, 2, 3 plus H squared Kt square upon twice MC. Means q could be integer here as number of points, since the dimension this q depends upon the up to how much extent we have reduced the bulk material in the z directions. Okay, and if you will plot this, then the graph will be discrete. For q equal to 1, we will have the different graph. For q equal to 2, we will have the different graph. So if this is the row E, so in earlier case, I used to draw the density of a state like this one, but now in this case, the density of a state will not be a continuous, it will be a discrete. It will be for discrete. For E equal to q equal to 1, this will be a constant density of a state. Means from this point to this point, there will be a constant density state. And if q increases, then it suddenly increases, and again we have a constant energy state. This is for E equal to q equal to 2. So what we have seen that for quantum well structures, when we have changed the bulk materials into a quantum well, means by repeating the dimensions in any one direction, either x, z, or y directions, then this continuous density of a state changes to the discrete density of a state. Okay? So this is the major changes, and this changes the behavior of the materials. And this density of a state will decide the device characteristics and performance. So whenever we select any materials, its dimension is very important. So nowadays, since the conventional MOSFET, we cannot decrease its channel length up to less than 100 nanometers. So emerging devices came like JLT, junctionless transistors, FinFET, TFET, right? These are the emerging devices. So in this, once you decide that these are under nanometers, so whenever you decide its thickness, you have to apply the modeling accordingly. Since you will take the thickness of a quantum well and you will apply a modeling, means you'll apply equations related to the bulk materials, then you will not get the desired results in the simulations. Right? So whenever you simulate something or whenever you design some materials, always take the dimensions in a proper way and apply the different modeling in the same way. And what are the applications of this quantum well? So in tunneling of electron, like tunnel FET, TFET. In TFET, what do? We do the tunneling of electron, means there is a barrier. Suppose this is a barrier. Electrons are present at this point, and electrons want to come toward these points, but this barrier is there. Okay, so this will not move like this. It will just tunnel through the barriers. That is called the tunneling. Okay, based on this, we have designed a tunnel for electrons. In this, the sub-threshold slope, thus sub-threshold slope is very less, and therefore the switching rate of this TFET is increased. So here also we can use the quantum well. Another well examples of quantum well is a quantum well laser. Quantum well lasers. So what it do? It is a semiconductor. It is semiconductor double heterojunctions. Where the thickness active layer is less than the particular wavelength of electron. Okay, so in this laser, what happens? The band gap, since the laser mechanism, it depends upon the band gap that we know. One thing I have not discussed, the applications of direct band gap and indirect band gap. Direct band gap and indirect band gap materials. So, in indirect band gap, what happened? Suppose this is your conduction band and this is your valence band. So topmost of valence band is this point and bottommost of your conduction band is this point. Okay, so the value of K at this point is something different, K2, and value of this point is K1. So these are called indirect band gap materials. Okay, so once electron from this point will try to come at this point. So in this way, the difference in this energy is released in the form of heat. Okay, but in the case of direct band gap materials, where the lowermost point of the conduction band and the highest most point of your valence band lie in the same line, value of K is same for both the line. So in that case, whenever electron from this point will come to these points, then this difference in energy is released in the form of photons, in the terms of light. Okay, so suppose this is the difference between this point and this point. So the wavelength will be how much? Hc by Eg, this gap. So depending upon this value of this energy difference between these 2 points, different colors of light can be emitted. Okay. So in earlier days, we don't have that much facilities to have different colorful light. But nowadays, we can find that LED having a different colorful of light. That is because of this band gap engineering. We can have different band gap. We can change this band gap. Okay. We can change this band gap. So effective band gap can be changed in the quantum well laser. Effective band gap changes. So the emission of wavelength also changes. So the emission wavelength also changes. Okay. So in this quantum well laser, generally we take as indium gallium arsenide versus indium phosphate. This is the combinations of two semiconductors. So with the change of this concentration of these 3 elements, this band gap changes, and therefore we have the different colors. So benefits of this quantum well laser is that we have a lower threshold current. We have a lower threshold current. Lower threshold current. Okay, and this is also less sensitive to the temperature variation. Less sensitive to the temperature variation. also has a high power. So there can be n number of usage of quantum wells you can use. And quantum dot is used in the cellular automata nanotechnology. Quantum dot is used in the cellular automata nanotechnology. Right, since we know that the CMOS technology has reached to its fundamental limit, that the Moore's law, and the power dissipation is also high, and fabrication cost is also high. So we can use this quantum dot cellular automata to design different types of logic, like with quantum dot, like this type of configuration can be termed as logic 0, and another configuration can be termed as a logic 1, like this can be termed as a logic 1. So we can design a number of designs using this quantum dot. And quantum dots can also produce distinctive colors. Determined by the size of the particle. Okay, so nowadays compounds like organic luminescent materials used in organic light emitting diodes, quantum dot based materials have purer colors, means it has a better colors, longer lifetime, it has a purer colors comparing to the OLED. Longer lifetime. Okay, lower manufacturing cost and lower power consumption. Lower manufacturing cost, lower power consumption. Okay, so these are the applications of quantum dot and the quantum cells. And nowadays we are moving towards, since we have seen that there is a huge benefits of using converting a bulk materials into a nano quantum wells or in the dimensions of the nano size. So nowadays we are moving towards the 2D materials. The graphene is one of the most used. Okay, so there are n number of 2D materials and n number of ways to characterize that materials. So that's all from my side. If you have any doubt, you can ask.
Then you said in quantum well,
direction
Yes.
energy of states will reduce in only one direction. Sir,
Right.
in what direction? X direction, Y direction, and Z direction.
Any direction you can reduce, any one directions.
Okay.
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 Whatever I have discussed, I have reduced in the that directions.
Yes. So, is there any effect if it change the direction in X, Y, or Z?
Yeah, it will have the effect. That depends upon how you connect that materials with other materials, right? Suppose you are making a channel length, okay, and you are decreasing its dimensions in the this direction, right? Suppose we have reduced this in this way. There is a gate, so its effect will have different, right? And if we will make the channel like this one, okay, so if this way, so both will have the different mechanisms, okay, in which way we are connecting with the different materials, right?
Okay. Thank you.
Any other students, if you find any difficulties in this semiconductors or its applications, or to sometimes you are very confused that which materials we should use for your applications, okay, so in that case, first go through the material property, okay, and then you find that which material suits your applications. Since now we have discussed that each material has a different band gap, each the materials have the different mobilities, scattering time rate is also different for different materials, okay, so we have to very take precautions at the time of choosing your materials for your applications, and dimensions
Okay.
is equally important.
Okay, so if there are any more questions, then please you can ask the questions. If you are having any question or doubt, please go ahead. So I guess there are no more questions. So uh, thank you very much,
If
sir.
they may have any doubts in future, they can also write an email to me, and just I will clear their doubt.
Okay.
It was a very basic about the semiconductors. Thank you, sir.
Yes, sir. So, first of all, I thank you everyone, all the students, and thank you, sir, for accepting our invitation and giving such a beautiful talk. It was really very innovative from basics to advanced level about the semiconductors. So, it was very nice talk presented to our students. So, on behalf of ECE department and BCE Bhagalpur family, I thank you. And we would like to be connected with you in future as well, and uh,
Sure, sir. Sure, sir.
so thank you very much, sir. Thank you all the students.